through Swarthmore College and University of California in Berkeley, and you're one of the open source developers for Xarray. I appreciate that so much. Got me through, a lot of my own research back in the day. So thank you for that.
So good to hear that.
And now been at Google for almost 10 years, I think. So very, very good. All right, I'll hand over to you then, and I'm excited to hear about NeuralGCM.
Awesome. Yeah, so excited to be talking to all of you today. I would love, I have some slides, but I would love for this to be a little bit interactive. So if you're on the, if you're sort of seeing things live, if you have, please, if you want to sort of throw a question in the chat, and I'm also happy to kind of get into a discussion as well. We don't have that. It looks like there's only about, we've got like 20 or so of us on here, so that's not 30. No, it's growing, but it's not a. Hopefully we can make this a little bit interactive. So I'm going to tell you about a project that my team at Google's been working on for the past. We've been working on for the past few years. And this is a weather and climate model called NeuralGCM. That's a neural general circulation models. And this is a collaborative project we did with a bunch of others. I'll sort of throw this up really briefly, but a bunch of others from Google and also some collaborators from ECWF and MIT. So big team effort. And today I'm going to talk about, first kind of lay the groundwork here and sort of give sort of my perspective on kind of where we're at a pretty exciting time in sort of the rise of AI as for weather and climate modeling. I think also more broadly for science. I think deep learning has been like extremely powerful, and I think that the trajectory seems to be only accelerating. So it's quite a time. It's quite a time to be working in science. I'm going to tell you a little bit about what makes NeuralGCM special and sort of the modeling approach that we took, which is a hybrid model that's physics and AI. I'm going to talk about some of the results in NeuralGCM. I'm going to sort of focus on our results for climate modeling and kind of zoom out and talk about sort of broader perspective on what sort of AI native climate modeling might look like. Because I will start with sort of the AI revolution in weather climate modeling. Okay, so first, we've been using physics for weather and climate simulation for a very, very long time. In fact, this is really one of the very first use cases for computers was running weather simulations, going back to like some of the first, so the very first digital computers. Now, like, I guess that's almost 80 years ago. It's been a good run for weather forecasting. I think that something that we may not all appreciate today is that weather forecasts now are a lot better than they used to be. And so this is one chart. This is assembled by some folks at this European Weather Center. They look at the accuracy of the weather forecasts, and this bar here, say call like an 80% forecast today. So roughly 80% accurate is kind of like pretty good answer, and we can now get that. Today we have say a 7-day accurate forecast that's equivalent to like about what we had is maybe like a 3-day accurate weather forecast of 40 years ago. So that's a pretty good track record. And there's a lot of things that go into this that have gone into like the weather models becoming so good. A lot of it, there's the compute, of course. The models themselves have been sort of are better as well, and of course data is also dramatically better. I think data is actually the biggest contributor to this gap here. This is actually northern versus southern hemisphere, and sort of the arrival of satellites was like a really big contributor to the improvement of weather forecasts in the southern hemisphere and kind of balancing that out. But it's weather forecasts with this paradigm have worked quite well. And it's been sort of a slow, I'd say, really a slow and steady pace of progress. There's a nice paper on this called the quiet revolution in weather and numerical weather prediction that sort of lays out sort of like the history here. And I think that AI has arrived now for weather forecasting. I think it's been anything but quiet. It's been a pretty loud. And so I wanted to kind of take you back to roughly to when we started this project, in like back in 2021. And AI was not really a thing for weather forecasting. There had been a few early efforts to explore building AI weather models. But if you looked at the accuracy of these models, they were a lot worse than the physics-based simulations. And they were like, I mean, like maybe around like twice the error, which is quite bad. Again, this is like going back to like I don't know, maybe like a weather forecast from like the 1970s or something. So no one was really taking it seriously. And then but people things changed, I think, in 2021, 2022, where kind of a steady stream of different sort of advancements from people who really knew how to use deep learning and sort of trained like large scale AI models on on historical weather data sets, were able to build sort of pure AI approaches that turned out to actually be able to match and now are starting to exceed the accuracy of the best physics-based model. So this is pretty exciting. I think a few of these breakthrough results were the Pangu model and the GraphCast from my colleagues at Google. This was at the end of right around the end of 2022. And so the past, now it's been, I guess I should add another year onto my chart, but the past 2 or 3 years have been pretty exciting. There's been a real explosion, actually, of different AI weather models. I think now there are probably more state-of-the-art AI weather forecasting models than there ever were physics-based models. And NeuralGCM, which is what we're going to talk about today, is one of those. And by some measures, it's a very competitive weather forecasting model. I think the more exciting thing is actually that we've also started to use it for some types of climate simulations as well. So I'll kind of get into what the difference between like weather and climate and what that means a bit later. We published this and we published this last year in a paper that was published in Nature. Okay, so I want to kind of start by talking about, I guess, why, like, kind of big picture, what sort of the modeling approaches that we were looking at here, and what we were kind of the inspiration for this work, and sort of laying out the big. We have, on the one hand, we have these pure machine learning approaches, and these are sort of here. It's like imagine you replace replacing all the details in the weather forecast with just some big neural network of some kind. There are a few different approaches. There are like graph neural networks. There's more like transformer models. There's diffusion models. I mean, it's like a very long list that's kind of growing longer and longer by the day. It's kind of, there's not one architecture that seems to be like totally dominating, but and these approaches have the strength well, a few things. One, they are pretty simple to write, not a lot of code, like thousands of lines of code instead of hundreds of thousands of lines of code. They're optimized directly based on data. You don't actually have to know a lot about the problems that you're solving necessarily. You don't have to have a lot of domain knowledge to build these models. And in fact, there are a lot of details. If you look at the papers where you look at this, if you have a bit of like meteorology or climate expertise, you look at that and you think like, that's really weird that they use that as like a predictive variable. Like, that doesn't make a lot of sense to me. But turns out you kind of throw all the data in the bucket, and the algorithms can sort that out largely. And that's because they're directly optimized for forecast accuracy. The algorithms are sort of like, as long as you have the training data, and we actually have some really great training data sets for weather that are based on sort of reconstructions of historical weather data over the past decades, that's used with a combination from observations and some with guidance from physics-based models. Just having the data, you can optimize directly for what you care about, which is very different from the physics-based approach. The traditional physics-based approach is you're solving a bunch of equations on a grid over the Earth, and you know the equations to solve. but there's a lot of them, and there's a lot of details that turn out to be really critical. It's not just like, it's one thing to think that, oh, I just have like the set of I know the equations to solve, and I just have to like solve some equations. But it turns out there's a lot of challenges there because we can only approximate the equations on the grids that we solve. We'll kind of get into this later, but there's also a lot of processes that are hard that we don't really have good equations for. Things like, and kind of the big examples of that would be things like clouds and rainfall, for example. Still, we can kind of build in all the physical principles, and we believe that the physical principles should hold in a very general sense. So it's actually, in some sense, kind of miraculous that the physics-based models get the right answer, because they weren't really trying to get the right answer. They were just trying to build a model of how we think the world works. And it turns out that also lets you make that also, it seems to be fortunately, our models have predictive accuracy as well, but they weren't directly tuned for that, or at least sure, okay, some of the parameters are definitely tuned to make them more accurate, but the sort of the modeling approach is really principled. And so our hope with NeuralGCM is it's something in between, and this is not entirely an original approach, although then we were able to get this to work pretty well for reasons that I'll explain shortly about why it's worked very well for NeuralGCM. And what, but here, what we're doing is we're blending together some of the physics-based and the AI-based approaches. And particularly, we're going to use the physics-based approach for the places where we know the equations to solve, and we know how to solve them, and we believe that we have a very good sense that from our understanding of the domain science that this is like the right modeling approach. And we're going to use AI for the sort of the hard to model processes. And typically in weather and climate models, that is the subgrid scale behavior. If our grid cell in a weather or climate model is typically on the order of 10 to 100 kilometers on a side, the smaller scale behavior is where so anything below that we're not really solving exact equations anyways. And that's where the AI can be most effective. Okay. Okay, I've already been telling you a little bit about what we've been doing with our hybrid modeling approach. Let me get into the details. Okay, so what we did is we took the framework of traditional weather models, so general circulation models, so they're called, and we decided to, and so we're still falling within that framework. And the key thing with the way that the general circulations model work is that they actually divide the equations that are solved into sort of two categories. The first one is called dynamics. That's what I have on the left here in the big yellow box. That's like a really big fluid dynamic simulation, and we keep that part in NeuralGCM. We actually rewrote that in Python, and I'll sort of explain why shortly. But we wrote it in Python and JAX. That lets us run the whole thing on GPUs or TPUs. Also, it's optimized through the whole system. And then we're going to replace sort of a large part of the weather model, what is called sort of confusingly, it's called the physics of the model. That really means only sort of parts of the physics. And these are the small scale processes like solar radiation and clouds and rainfall. And there we're going to use a neural network. And we're going to kind of blend together the two things inside the differential equation solver to sort of advance forward autoaggressively in time. So it still looks a lot like so what we have here, it looks really is within the framework of the way that we understand how to build, sort of from scientific knowledge, how to build models of the Earth's atmosphere. And so the state of the system very much is the exact same state that is used in a weather climate simulation. And again, we're learning the small scale features here, the stuff inside a single grid cell, the processes that are processes like small scale, like clouds, which is just impossible to simulate with full fidelity, even if we knew the exact equations to solve. We don't have the data on the data on these small scales. We don't have the power to simulate it. There's like a lot of sort of parameters that one might need to tune and so forth. It's really complicated, and there's a lot of, so we're able to lie to a lot of that detail with machine learning from large data sets instead. And then I'll talk a bit about kind of how we built this on top of JAX. And I'm happy to also, I think this is my main slide on this, but I'm also happy to kind of talk, as someone who's done a lot with JAX and scientific computing, I'm also happy to sort of talk about this more later as well in the Q&A. I think JAX is a really fantastic tool for building scientific computing, and that's really what it was. I mean, so it was built for, of course, for training neural networks, but almost all of the principles that make it a fantastic platform for building neural nets also make, in deep learning, also make it a fantastic platform for scientific computing in general. And so I'm going to go through a few of these, and so kind of like the key features. The first one is on the left here, is that we have XLA compilation. So this means that the code that you write is sort of compiled into a low-level machine, into a sort of a low-level machine code. That's what XLA is, and it's just-in-time compilation. So that means you can write Python code, and it's optimized and runs at the speed of really sort of maxes out your machine's capabilities like compiled code. And it also critically means that what you write is also can also be executed on the GPU or TPU as well. And so we can sort of take some code that you write, like sort of NumPy Python syntax, and it runs on, and now it runs really fast, and it runs on machine learning accelerators. So that's great. We can, of course, so we have high performance. We can calculate gradients automatically. We don't have to write how to optimize through our code. And I'll kind of show this, I guess, why this is critical for NeuralGCM. But this is the key, kind of in some sense, is arguably one of the most critical parts of deep learning, is that you can tune all the parameters in your neural networks. It's also useful for tuning the parameters in your sort of scientific programs. Either if you have sort of like hybrid approaches like NeuralGCM, where you actually have neural net parameters in there, or even if you're just trying to optimize other parameters. So for example, in a weather climate simulation, one of the big challenges is say, what is the state of the what does the state of the world look like based on a bunch of observations? And the way that's a problem called data simulation. And the conventional weather simulations actually also use like gradients to sort of optimize the state of the world, but they mostly use gradients that were written by hand, and so that's like a huge amount of work to kind of maintain these separate, so the whole separate basically duplicate code path that like runs in reverse and calculates gradients. And so in JAX, that's very easy. And then kind of continuing sort of left to right, we have vectorization. I can show you some examples here, but this is basically a much less painful way of writing writing code than using, basically you can write all your code like on scalars and vectors, and it sort of automatically adds an extra sort of vectorizing over additional dimensions. So you don't have to rewrite your code. If you say want to handle a batch of examples all at once, you just do this transformation, and all your code, you get very efficient code that runs, that where you add extra dimensions, but you don't have to think about the complexity of the extra of sort of writing the code like that directly. So like really fantastic. We can do, again, we have efficient sort of transformations for, this is, I guess maybe sort of table stakes, but sort of looping through time. There's all sorts of fancy tricks, it turns out, when you actually calculate gradients. We do automatic differentiation for optimizing programs that you wouldn't necessarily know if you just use these tools out of the box. And then one of those is absolutely like critical, essential, if you're ever doing something like doing a big physics simulation in time, is gradient checkpointing, which I'll just sort of throw out there. I'm not going to, if I can give you some pointers if you're curious about it, but you should look it up if you're doing anything like stepping forward in a big loop and optimizing other parameters. It saves you a lot of memory. And then the last one here, which is also really critical, of course, for JAX, is model parallelism. And JAX has some really fantastic tools for both sort of automatically parallelizing your code across a bunch of machines, and also, but while still giving you the control to go in and like adjust the little parts where the compiler didn't get it quite right. And so that mix of explicit and implicit parallelism is extremely powerful. It took us about only like less than a month to take NeuralGCM from something that ran on one GPU or TPU to something that ran where we're doing training on 100 TPUs at once, and that's including a lot of really complicated model parallelism that across 3 spatial dimensions and like neural and like examples and neural nets. I mean, like a lot, like something that you would writing an MPI, for example, would be much slower. So, anyways, this is my pitch on JAX, which I love, and I've made a number of contributions to. Okay, so I think JAX worked out really well for us. Let me tell you about what's different about NeuralGCM from a modeling perspective. And the critical thing here is that we sort of bit the bullet instead of we're going to rewrite the whole thing in JAX actually. And that's because, and so let's look at how people have tried to train these models before. And that is taking a sort of traditional physics simulation, which is like a really big clunky thing. It's like a million lines of Fortran that like, and if Fortran means anything to you, and like that's this is like very hard to even understand what it's doing. And so there's kind of this notion of like, well, this is like we have to, but it has a lot of really good stuff in it too. So how can we sort of fix this up? And traditionally the approach is basically you run that simulation, you get some outputs, and you're like, I want to fix things up. Let's say I know that I have some sort of ground truth. Maybe it's a higher fidelity simulation that I ran, or some sort of observations, and I want to use a neural net to kind of correct the outputs of this model and sort of step forward in time. And so, in principle, this is a totally reasonable thing to do. The structure looks very high level to what we did in NeuralGCM. The challenge, though, is that what you use these models is very different from how you train them. In particular, you train them, say, one time step in time, or say like just predicting like one quantity that the model. Like one updated quantity that sort of correcting some output of the model. But when you use them, when you use the models, you do inference over many time steps. And whether in climate models, it is common to run models over hundreds, thousands, tens of thousands, even millions of time steps. We have to take very small time steps in these models, typically like on the order of minutes, and you want to simulate out for maybe for weeks or years. And so the models can actually go really haywire when that inference because of this difference between what you trained for and what you're testing for. And in fact, a lot of these models, you train them on and the model like immediately and you run it and the model immediately like explodes basically. Like the simulation becomes so bad that it becomes numerically unstable and you just get NaN everywhere. This is, in fact, I think like probably the most common thing that happens when you do this. Not always, but I talked to a lot of scientists who have been really rather badly burned by this. And so this is again not a new idea. Some people managed to get this to work, but largely a very unreliable process. And what we did is again we're going to write the whole thing in the neural network framework. We write it in JAX. And that means that now we have the ability to do automatic differentiation through the dynamical core, as well as the neural network part, the whole thing. So now we can optimize the whole thing end to end based on data. We can train it a lot like how we train, how like these AI weather forecasting models are trained, in that we're not just training it on like predicting stepping forward like 10 minutes into the future. Nobody really cares about a weather forecast plus 10 minutes in the future. But what is quite interesting is if you can make a weather forecast, obviously that, say it goes out for a whole week. So we can train this, we train NeuralGCM on doing tasks like making a 1 week weather forecast. And so now we have the training and inference is like largely the same process. And that means we get that we get sort of the generalization that we care about. And this really helps a lot for getting good online performance out of I think in our case, I mean, definitely if we train it on just a few time steps, the model definitely does not work. We had to train it over many time steps, and that's because I mean I could get into the details, but like the equations of the Earth's atmosphere are not very stable. So it turns out you really need to take care when you tweak them. You have to kind of see. It's not obvious if you tweak the conditions a little bit what's going to happen to the physics part of your model. And so to avoid these bad feedback loops. All right, so that is the overview of what we did with sort of NeuralGCM, kind of how we set up the models. Let me talk a little bit about how well this worked for some climate and weather simulations. I already showed you earlier that we're kind of at sort of roughly at state of the art for weather prediction. Let me say a little bit about what was special about NeuralGCM compared to some other AI weather models, especially some of these early ones. The GraphCast is pretty old now. It's kind of one of these first ones. Is that it's, if you look at, there's this aspect of like physical realism. It's sometimes a little bit hard to quantify, but is actually really critical for both weather forecasting, especially for climate modeling. And if you look at something like on the left here, I have, this is an image. Actually, this is like a plot of specific humidity. I think this is actually over Australia, so very appropriate for this talk. You've got lots of interesting clouds down there in the tropics and in the southern hemisphere. And if you look at like what the ground truth, and it looks something close to this image on the left, there's a lot of detail and a lot of variability. And even in like a 10-day weather forecast, like you're never going to get that right, because some of this variability happens due to sort of very quickly evolving like weather systems, like convection happens like within a single day. Like it is literally impossible to predict this. Like how to make a perfect 10-day weather forecast, of course. So the question is, what does your model do when it gets the forecast wrong? One approach, this is what you see on the right side. This is a pure AI approach, GraphCast. It was just optimized to produce like the minimum like mean squared error of the values at every pixel. So you see at first it's very sharp, but when you run that forecast out, now you're at 4 or 5 days. Now the model, it's kind of hedging its bets. It says, well, I can't, like nobody can predict, say what exactly where the clouds are going to be 10 days in advance. So I'm going to predict like an average. And the simulation, the result now looks, you still see some features like on the right, you still see there's like an evolving like weather system at some points, but basically it looks like a very smooth plot. And if you run it out beyond 10 days, it would get even worse. So I mean, eventually it becomes sort of like really smooth, or the simulation sort of drifts out of, like it looks so smooth that the model doesn't even know what to think, and sort of, and again, like becomes like numerically unstable a lot, and like blows up at some point after maybe some number of weeks or months. And in contrast, we spent a lot of time sort of building NeuralGCM to be something that produces realistic looking examples. And I could talk about sort of like the training strategies we use to do this, but basically the notion is that like in some sense that with NeuralGCM is that if you can't, if you don't know the right answer, instead of producing like an estimate of like average weather, produce a single sample, a realistic looking sample of what weather could look like. And we have, and in fact, like many of our models, we build sort of these ensemble prediction models where we can sample out many realizations of what weather could look like. And this is much more useful from a climate, sort of a weather, I guess, from a weather climate modeling perspective, as you get beyond, say, like a 1-week weather forecast, because there is this uncertainty, this intrinsic uncertainty. And so I'll tell you a little bit about what we use, how we use this. For, again, like what it means, like say in a climate simulation. So we can do things like run the model out for an entire year, and we can track. And when you run a 1-year simulation, you still see that the model produces extreme weather events. So instead of just being everything average weather, it produces tropical cyclones, for example, and you have about the right number of tropical cyclones, and about the right areas, like about the right places on Earth at about the right times on Earth, and like you can sort of sample this and say like, oh, here's what a here's what like a hurricane season might look like, for example. And this is the sort of thing that is, again, for sort of exploring like what if scenarios, for like understanding, like getting towards sort of climate modeling is that's like really critical. What we also found with this is that we can calculate the errors of these models, and so that the over climate timescales. So again, something like run the model out for a few years, calculate the error in the model in terms of compared to leading climate models, in terms of like and typically the climate modelers care about things like the bias of the model. So on average, how far off it is. And this is sort of one example of variable that we looked at. This is the total amount of water in the atmosphere, and we're able to get we found that the error on NeuralGCM was about 30 or 40% less than this GFDL model, which runs at a much higher resolution, and it's much more computationally expensive. This one runs, we can simulate 200 years in a day. This one we can simulate about like 0.05 years in a day, and this one again runs on one Google TPU. That's like you rent it for like $1 an hour or something like that in the cloud. This is like a whole substantial like CPU cluster, like 10,000 plus chips. So it's kind of a dramatic difference in potential cost savings here because these models are like run so much faster. This is like something like 100,000 or a million-fold difference in compute. Yeah, I have those numbers here. Okay. And then what we also did with this is we ran this out for, again, for sort of multiple decades as well. So here, again, something I should clarify is that we only are modeling the atmosphere. So as those of you who are climate scientists will know, this is only one part of a climate model. You also need to model oceans and ice and lots of other processes. So we do this sort of atmosphere only comparison. That's a pretty standard setup for climate models. And we do prescribe sort of observed ocean temperatures here. But interestingly, even if you compare to the other climate models, the other atmosphere only climate models, we track the temperature here. This is sort of surface temperature averages much more closely to observations than the average of even the whole ensemble suite of different atmosphere only climate models. It's much closer, and so that I think is pretty exciting from a perspective of, again, potential to kind of make climate models much better. And then I'll mention one other thing. This is pretty recent. So more recently, my team has been working on sort of extending this approach to modeling sort of satellite-based precipitation. And so we have a preprint on this. We released open. This is all, I should say, all open source. So this is and sort of permissively licensed. And so we kind of threw this out there on GitHub, and then some academics at the University of Chicago we're interested in making better forecasts of the Indian monsoon. So the monsoon is like probably in many parts of the world. It's basically when the rainy season starts, and this is like in the tropics. This is like absolutely critical to any sort of like rain-based agriculture, and it's like probably one of the most impactful weather events on Earth, particularly in India. And so this group sort of tested a bunch of AI-based weather models. The monsoon you won't need to predict. Ideally, it is somewhat more predictable than other weather events. So you can predict it out to 3 or 4 weeks in advance potentially. And they found that NeuralGCM performed very well for this. And they actually used this year to do sort of operational monsoon forecasts that were sent out to about 40 million farmers. So we were pretty stoked about that. Okay. So in summary, we built this hybrid ML and physics model of the Earth's atmosphere with state-of-the-art accuracy. And it has a lot of strengths. Again, really nice like weather forecasts. I think one thing I didn't mention, but this is the first weather model to beat the sort of best physics-based models for 15-day weather forecasting. On sort of probabilistic forecasting. It has these sort of very competitive climate simulations. It's a lot faster and cheaper and sort of also much simpler as well, a lot fewer lines of code. It's not yet a full climate model, but it's, I think, hopefully a really helpful step in that direction. There's still a lot more work to be done to kind of fully land this, but for the climate models of the future. But I think it's a pretty exciting proof of concept. Now I want to take a step back and talk about sort of lessons from my experience here for like sort of AI native climate modeling, and then hopefully this will probably be another 5 or 10 minutes, and then we'll have some time for Q&A as well. Okay, so again, I want to kind of recap this here. This is like a nice sort of infographic we made, but I think pretty compelling here. I think this is true for my team's work, and there've been, I mean, since this paper came out, there's actually been a whole handful of other versions of sort of AI-based sort of climate model emulators. And these models are incredibly fast in comparison to traditional physics-based models. And that, again, it's a mix of two things. One is that we run it on a GPU or a TPU. And secondly is that we can get accurate simulations with AI using much coarser grids. So we have just like a lot fewer numbers to throw around. And the more the more like the finer your grid resolution is, like the slower your simulation is, and the more computers you need to distribute it across. So it's a lot faster, and that potentially opens up a lot of exciting possibilities for using these models. It is way easier, I think, almost indisputably, to sort of just to download a model like NeuralGCM. You can run it on your GPU. If you're a researcher, like this is fantastic, because otherwise these accurate traditional models are just like, they're just inaccessible for many scientists. So it's like really limits what you can do and explore, because they're so slow and you need like such a large budget to run them. The other thing, I mentioned this briefly, but I think this is a really critical thing. Probably, perhaps one of the most important advantages is simplicity here, and in the sense of like how much code goes into these models. And NeuralGCM is about 20,000 lines of code. I mean, it's a bit more, maybe a second book if you include how the model was trained. But this, I mean, that's about as much lines of code as fit in a textbook. Whereas a traditional weather and climate model is more like 1 million lines of code. Actually, I showed this to some climate scientists this summer, and they're like, "Well, I wish my climate model was 1 million lines of code." Actually, like CSM, which is one of the leading climate models, is 5 million lines of code. It's like, it's not just it's like the whole bookshelf, it's like the whole library basically. You would spend your, I mean, you can't and do like, I mean, spend your whole career to kind of like learn how these models work, and even then, they're just really complicated and challenging to build on. And so this is, yeah. Yes, we will, Scott. I will. would love to get into that a little bit. I'll touch on that. Yeah. Yeah. So I think simplicity is one key advantage. I mean, I will say that one thing that gives me a little bit of hope about is actually sort of like modern AI tools like LLMs, which turn out to be a lot better at scalably writing code than most of us. And I think those of you who are writing code have probably noticed that we can write code a lot faster, even like this year versus last year. I mean, at least I feel a lot more productive. So I am pretty excited about maybe 1 million lines of code will be less intimidating than it used to be, but that's still a lot. I'll say one thing is that I do think that even though some of the pure AI approaches have also been effective for some climate modeling, we really do need physics to some extent. And I'm going to mention one process. I mean, but there are others, but there are many things in the world where we do not have data. We only have model. We only have like we sort of have it like in sense of like. And if we try to learn things just from data, we don't, like, there's kind of no hope. And one example of this is levels of carbon dioxide, which of course is a greenhouse gas that leads to that is one of the main causes of global warming. And greenhouse gases like CO2 is mostly constant over like around the world. And so basically we have never seen, this is from a few years ago, but we've never seen levels of carbon dioxide that are like, significantly, that are like off the charts here. And so if you ask the AI model to sort of predict how the Earth behaves under those conditions, there's kind of no way it could get that right. So some of these processes, especially processes where we don't have data, cases like what does the Earth look like when everything is 2 degrees warmer, when it's 4 degrees warmer. I mean, like techniques like NeuralGCM like AI models can be helpful here. I mean, if they're built the right way, but really generalizing is tough. And again, I think it's much more helpful to think of the right modeling approaches as a spectrum, where depending upon how much you care about interpretability, how much you care about how much you care about sort of generalization, like how good your do you have the training data sets? We can there's a lot of room in between the extremes of pure machine learning and pure physics. There's not one right answer. I think especially for science, we need to kind of get out of this like AI versus physics mentality and think like AI and physics. And I think that's clearly that is clearly the future. And kind of like, lastly here, I'll just mention, but I'm actually quite excited about sort of like LLMs and agentic AI. And I'm sure that many of you are sort of following this, at least, I mean, at some level of engagement. But in San Francisco, this is like the world out here. I mean, everybody, it's kind of crazy. It's like sometimes it feels like we're living in a different universe. And I'll just say that like some of these things people are already doing, and I think other things that people will be doing very soon. Like, I mean, particularly when it looks like things like we spent a lot of time to convert. Like probably there's like, I mean, at least like someone on my team spent about a year, roughly, maybe even like a couple of people, to convert big legacy like a Fortran code, not even that complicated of a Fortran model, into Python. And I think today with large language models, you could potentially do that much faster and more effectively. And sort of automate many of those processes. In fact, I know some climate scientists that are starting to do that with like very good results so far. I think it's very likely that these models AI models could be automatically analyzing outputs from climate models, and if climate models, like especially the AI ones, are fast enough to design and run, it is not crazy to imagine these tools turning out to be incredibly powerful tools for sort of automatically tuning and building these models too. And if you believe the folks, again, the sort of the buzz on the street in San Francisco that AGI is just around the corner, we could be in a very different place just a small number of years from now, in terms of modeling capability. So this, I think, definitely really critical to keep an eye on. So okay, so maybe I'll kind of close here. I have some references with this work, and maybe I'll answer Scott's question as well about kind of where we're going. So what we've done so far, I mean, we have, it's not a huge team at Google. There's about 4 of us working on this. We are continuing to develop this. We open sourced it. We've spent a lot of time working on turning this into, initially I'd say it was more like a proof of concept. Now we're trying to turn this into something like a really firm foundation that people can build upon. We have sort of a new version of our sort of modeling framework that we're going to be releasing a bit later this year that I'm quite excited about. I think like is a much better building block for people to extend, and also to really work with others, because it turns out the atmosphere is big, but the whole Earth system is much bigger, and this is not something that we're going to be able to do that we have any hope of really doing sort of on our own, especially when it comes to sort of understanding the future of climate. It's just like there's just many domains of expertise, like again, things like oceans and atmospheric chemistry and ice, and sort of all the land surface processes. We've been starting to explore how to sort of couple these in with models like NeuralGCM, and we've been working with a lot of academics who have been sort of starting to build like different sort of taking sort of this work in sort of different adjacent directions. But we are working towards this, but I think it's not something that we're going to be able to do alone. And so my hope would be that we can have something like a sort of an open source sort of collaborative environment for trying to build these models. But there's definitely a lot. I mean, I could get into some of the more specific technical challenges as well. But there's a lot of room for iterating and improving on these models. All right. Well, I guess we can open up for questions. Thanks for your attention, everyone. I don't know how you want to do this, Nathaniel.
So much. Yeah, if there's any questions, feel free to unmute or post one in the chat. Yeah, Chris, you've put your hand up. Do you want to? Here we go. There's a few coming through now. Yeah, Deepma, do you want to unmute yourself? If you can, maybe I can do it. Oh no, we can't hear you. Okay, we can't hear. Maybe post it in the chat if you can. Otherwise, Chris Bull, did you put your hand up? All right. How about Alan in the chat? How many weather services around the world are using this already?
Yeah, that's a good question. So it turns out, I think every weather, I mean, we think over the past few years, I would say, so there's like this as of like NeuralGCM, and just I think it's maybe not too many, though. I mean, I think some of them have been experimenting with running this. There are a lot of them that are now like building their own, and so I think partly inspired by this. So like ECWF, who we worked with on this, has they have built their own AI weather forecasting model, which actually went operational earlier this year, and that is I think this is very rapidly becoming a thing. I think almost every weather agency is sort of realized that this is actually really that this is something that they need to be part of. I mean, for climate modeling, that's still much more nascent. I think we're not quite there yet.
Good stuff. All right, and in the chat, have you compared this approach to DOME of the operator learning based approaches like ForecastNet and Pinos? I didn't quite understand
so I can speak a little bit on this. So there are some models. I think particularly ForecastNet is a model from NVIDIA. That's also, and there's a few versions of it. I think the recent version that was actually is in some sense kind of sort of similar to NeuralGCM, is using sort of spherical harmonics as the representation for learning, and that's also how NeuralGCM, how the physics-based simulator, how we solve the fluid equations as well. And that model also actually works very well. I mean, I'm not sure I've seen, like, I don't know if the accuracy has been sort of 100%, compared, exactly apples to apples, but I mean, they are also sort of like a similar ballpark. I mean, there are a lot of effective approaches here. I think it really depends for these sorts of, again, the sort of approach that you take. It really depends on the sort of the representation that you have. Yeah, but it's definitely possible to get very different modeling approaches working well.
Good stuff. And there's a question about the ERA5 data set, which is for your training data set. Will you always need the traditional physics model to train on?
Yeah, that is also a really good question. So ERA5 is this sort of the training data set we use. Almost all of these AI weather models use ERA5. It's from this European Weather Agency. It's based on the physics-based simulations as well, to like process observational data sets. I think everyone's the hope is perhaps no, we won't need this. I mean, I think there is some work. There's a paper that was like in Nature earlier this year called the Aardvark model that was based on observations. I think no one has really gotten it that has gotten models to work super well yet without using traditional models. I will say it's not clear. I mean, it's clear there are a lot of modeling challenges in doing raw sparse observations. But there's also a lot of challenges, like just like logistical challenges and like gathering together all the different raw data sets. And I think those are probably comparably large to the challenges of figuring out how to model them. So I think we will see. I mean, there are a lot of people in this field that are working on this challenge. And I think we will see a lot of progress on building these models from raw data sets. I think, but it's also really hard, and especially when you say I need. Say I want to train on 40 years of historical weather data. Now you have to gather observations from 40 years of the past 40 years, and that's not going to be the same. It's like satellites don't last 40 years, so like it's going to be like a whole different like observing network over the past 40 years, and that's like makes the modeling problem like quite challenging actually. But I would say I'm pretty bullish on that. Okay. I guess we can go to Dietmar's question.
Yep. What is your best guess timeline for presenting a fully coupled climate or ESM model?
Yeah, I mean, look, I think it's going. I mean, and for sure, we're also thinking about how you can couple this like to ocean general circulation models. this is not, again, not something we've done yet. I think this is not something we're probably going to be able to do on our own. I think we are exploring how we can make this happen. My guess is that I think that there already are some attempts at like some more pure AI approaches that are getting pretty close to this. Yeah, maybe the agents actually, like seriously, like I think that like if the challenge one is you have to rewrite your Fortran model into Python, for example, like I'd say for a long time that seemed like that was going to be kind of crazy. Now it seems like maybe that's not so crazy. So we'll see. I think it's going to be at least a few years. But there's enough interest in this that I think it's going to happen.
Fantastic. Any other questions come through? All good. Oh yes. Wait, here's a big one. Do you want to read that one?
Sure. I don't know, MM, if you want to unmute, you're also welcome to unmute yourself. But other areas of environmental science. Ooh.
Great question, like the geodynamic models and that sort of thing.
Yeah, I will say that I think that there are a lot of different models in science. So I will say that like my perspective maybe is a little different than some of what I don't think there's going to be like a single AI model that's suitable for all areas of science. I think that different models need sort of model sort of different things at different levels of fidelity on different space and time scales, and it just doesn't make sense to think about building one model for everything. So I think that probably the details are going to be different, but I think that at a high level, I think that some of these ideas and some of the trade-offs about like there's some parts of systems that we understand really well, and we want firm rules, and like that's like the laws of physics, and there are other places that are sort of more empirical and we can kind of tune based on performance, and that's like where AI is going to work really well. And there's like complicated codes that we can also use AI to help us write. Like I think that like some of these themes are pretty shared across a lot of areas, a lot of different areas of science. But probably the details and the models themselves are going to be different.
Good stuff. And now collaborations, are you open to those, or what? Contact you for more information?
Yes, please reach out. I think unfortunately we don't have a like the biggest challenge, I think I would say honestly, is that like it's like our own bandwidth for sort of taking part in collaborations is pretty limited, just because if I was doing collaborations, I could be spending like all day doing collaborations basically and not sort of get any of our own work done. And we also have other projects that we're trying to in this broader space about the potential of AI for science and weather and climate that we're pretty excited about. But for sure would love to if there's things that we can do to help, especially to like help accelerate your work. We are very interested in building this as like a platform that people can build upon.
Fantastic. All right, yeah, Chris asked the question as well.
Yeah, so I'll say coupling to an ocean. So we've been thinking a lot about this. I think that like one answer, one version of this answer, I will say for the specific version of NeuralGCM that we have so far, probably not. And that's because we didn't train it on, it doesn't take sort of fluxes from the ocean as inputs. It doesn't take fluxes as inputs. So like it's not quite formulated in the right way that you would need to couple. But in principle, would not be a huge challenge to sort of add those sorts of inputs. And we have done some experiments actually where we've sort of coupled NeuralGCM into a sort of an AI ocean, and we're able to get that sort of working reasonably, reasonably well. I will mention that I'll just mention that there was a recent paper from let's see if I can find this, but this was from some folks at the Allen Institute for AI and NYU who sort of did show they were able to sort of couple together again like a pure AI ocean and atmosphere model recently. So I think it is very much possible, and there's some interesting science challenges in terms of how you in terms of training models that work well across different time and space scales, and we are starting to try to figure those out. It's probably not going to work necessarily like out of the box, but I think that these are we will get there eventually.
Fantastic. All right, I'm just looking at your GitHub. It looks straightforward to install. Pip install NeuralGCM, and then a handful of lines of code to make a model.
Yep.
So hopefully everyone can get their hands dirty with that and report back. All right, everyone. I think that brings us to time. So thanks very much, Stephen, and yeah, excited to see what happens in the future. So thanks for joining, everyone. Thanks, Stephen.
Take care.
Cheers.